Welcome to the lecture for topic 4 of your summer assignment, part 2. This is all about specific synthesis and decomposition reactions. And depending on your foundation from first year chemistry, most of this might be review. But for some of you, this will be brand new. So you'll have to really focus on how to memorize and how to recognize the patterns so that you can remember what the products will be. You are, again, having hopefully already created your learning targets from this packet using these pages. And when you are finished, you will have some practice problems to do from that same packet. So really work hard at knowing how to determine what the products are and how to write the formulas for the products. This is great practice with naming and formula writing, as well as practice with using the predicting the products from different patterns. So if you haven't made your learning targets yet, stop the video here and then restart it when you're ready. Otherwise, you have made your own notes, you're ready to go on, so you definitely want to be adding my examples to them as you watch this lecture, and you definitely will want to refer back to these as you're doing the practice. Okay, so synthesis and decomposition rules, remember, are the backwards and forwards of each other. If something is a synthesis, then when you decompose it, you should get those two things back again. So this is like learning two sets of rules at once. And so for the easy ones here, I'm only going to give you the rule of binary salts this way, but for these easy ones that are binary salts made of two elements only, then what's happening here is that we can determine pretty quickly what's happening. This is going to be a salt would be composed of a metal and a non-metal. So when you're doing this, whether you're putting them together or taking them apart, the charges of the formula for the compound itself will have to be balanced in charges. So don't forget to do that. Also remember that a lot of these non-metals will be halogens or will be diatomics. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, perhaps hydrogen, all of those may show up in these reactions, and you have to remember that they are diatomic. You also want to remember that sulfur is S8 and phosphorus is P4, so these things are going to come into play. When you have a metal and a non-metal that you're putting together or taking apart, those are the things that you have to remember. So let's just do a couple of really quick examples. If I have magnesium, the metal is not diatomic, nitrogen, the non-metal is, so I have to write those formulas as Mg plus N2, and then in order to write the formula of the compound, I need to remember that once these are ions, magnesium will be 2 plus and nitride will be 3 minus, and so that means that I need Mg3N2 as the formula of my product, and then I'll need to balance with coefficients. So in this case, this is just adding a 3 in front of the Mg because the nitrogen's already balanced. We can do the same in reverse for aluminum chloride. Aluminum is a charge of 3 plus and chloride is a charge of 1 minus. So the formula of the compound that we're starting with will be AlCl3. And when it decomposes, it's only two elements, so it has to decompose into those two elements. It's going to decompose into aluminum, which is not diatomic, and chlorine, which is diatomic. And so now I need to worry about coefficients. So this would be, I need 2 there to get 6 chlorine and 3 there to get 6 chlorine, and then 2 there to get 2 aluminum. So these are the simple ones, all right? So you'll get some practice with this. If you do happen to have the decomposition of a binary molecular compound that's made of 2 nonmetals, then it will just separate. If you have 2 nonmetals that you are synthesizing together, hopefully you'll be given a clue about what the product is, because it's really hard to know what nonmetals will do to combine because they're not doing charges. You're not using charges to do it. Okay, let's look at some synthesis reactions now. We are going to synthesize hydroxides from a metal oxide and water. So this is going to be really important because when you see this, this is 2 compounds, and you need to make sure that you're not classifying this as a double replacement. All right, so water will not be the reactant in a double replacement reaction. Water is typically, when it's a reactant, it might be a single replacement reaction, or it will be a synthesis reaction. The other clue that you have is that we are not going to see oxides in double replacements. So when you have a metal oxide or a non-metal oxide plus water, this is a synthesis. Some vocabulary here. Your metal oxide is what's known as a base anhydride, because when it reacts with water, it forms a base. A base is going to have hydroxide at the end. Okay, so we can say that the metal oxide is a base that has not yet been attached to the water, and so we call it a base anhydride, or a base without the water. All right, so just kind of keep that in mind. That vocabulary is going to come back in later when we do double replacement reactions, and so I wanted to introduce it to you here. All right, so let's do an example of this. The metal oxide plus water gives us a metal hydroxide. The charge on the metal is going to stay the same, whether it's in the metal or on the left or the right. So let's go ahead and do this. Silver oxide, silver is a charge you should know at 1 plus, and O is 2 minus. So this means my formula is Ag2O. And I'm going to add water to that. And I'm going to form the metal hydroxide. So this would be Ag1 plus and OH1 minus. And so the charges are already balanced. I'm just going to leave it as AgOH. And then to balance the equation, I need 2 silver. That gives me 2 oxygen, but I have 2. That gives me 2 hydrogen. I also have 2, so the equation is balanced at that point. You want to memorize this, and you also want to memorize that if you have a metal hydroxide decomposing, you're going to get a metal oxide in water. So kind of memorize these backwards and forwards. Okay, let's talk about the synthesis of acids. This works the same way. A non-metal oxide is what we call an acid anhydride, because when it reacts with the water, it forms an acid. So you have to kind of keep this in mind. This is a little bit trickier, and we're actually going to talk about something called oxidation number in this, so that you can decide which acid is formed. The clue here that you have is that this non-metal oxide plus water is going to create an acid that has a polyatomic ion in it, because the non-metal oxide is basically going to react with and pull the oxygen off of the water to form that polyatomic ion. Okay, so you're going to end up with an H something, and this has to be a polyatomic ion. The oxidation number of the nonmetal has to stay the same in both compounds. So you don't know how to do oxidation numbers yet, and we'll learn this later, but it's essentially finding the charge of an individual element in a compound, even when there's more than 2 elements. And so what we're going to look at here is, we'll talk about that as we do diphosphorus pentoxide. Okay, so let's say that I have diphosphorus pentoxide. This is a molecular compound. It's 2 nonmetals, and so it's telling me it's P2O5. If I want to find the oxidation numbers, I'm finding the charge of the phosphorus and the oxygen. And you already know that oxygen in a compound, its oxidation number is going to be -2. Okay, so we're going to do this the same way as you would find the Roman numerals when you're looking for the Roman numeral on a metal in an ionic compound. So I have 2 phosphorus and 5 oxygen, and it has to equal a total charge of 0. So the 5 oxygen is 5 times -2, and that means that this is -10. So 2 phosphorus have to equal +10, because they'll have to give a positive charge. And I can do this algebraically if I'd like. I get 2p equals +10. So p equals +5. And this is the oxidation number. We don't need it for a Roman numeral, but we do need it because when we add it to water and we form an acid, I need the oxidation number in my acid to be +5. So you need to know a little bit about polyatomic ions here, and you need to choose whether it's whether this acid is going to be with phosphorus and oxygen, either PO4 or PO3. Okay, either way, I'm going to have to add 3 hydrogen. And when I teach this in first year, I tell you, pick one and try to balance the equation, because only one will work. Okay, so that when this becomes the compound, because the oxidation number has to stay the same, only one of them will actually balance as an equation. But let's look at oxidation numbers in here so that you can see how we would do this for real. Hydrogen's oxidation number is going to be 1 plus, unless it's with a metal, and it's not. So I have 3 of them here, so this is 3 times plus 1. And I have oxygen, 4 of them, which is going to be 4 times negative 2. And so right now, this total is negative 8 and positive 3, or negative 5, which means the phosphorus has to be positive 5. So this is my choice, okay? This is the one that's going to be the product. If I wanted to do the same over here, this would be 3 times plus 1 for the hydrogen, and 3 times negative 2 for the oxygen. So combined together, this is negative 6 and positive 3 is negative 3. That means the phosphorus would have to be positive 3. This is why I'm not using H3PO3, I'm using H3PO4 in my equation. Once I have the equation written, P2O5 plus H2O yields H3PO4, now I need to come back in and balance using coefficients. I see 2 phosphorus, so I'm going to do this. And that's 6 hydrogen, so I'm going to do this, and hopefully now everything else balances, because if I change something on the, again, it'll go around in circles. All right, so this takes some practice. You can always use the cheat method of let me put both of them in and decide, but this is the real way, and now you're in AP, so we'll do it the real way. Okay, those are probably some of the harder ones. Let's look at this. This is probably the hardest one. This is really the reaction between an acid anhydride and a base anhydride. And I have a metal oxide and a non-metal oxide. Again, this is not a double replacement. That's because these are oxides, okay? I am going to, however, form a salt that has a polyatomic ion in it. And so we're going to do the same idea, that in that polyatomic ion, the non-metal has to keep the same oxidation number, and the metal charge has to stay the same. So let's come in and see what we have here. We have copper 2 oxide. This would be Cu2 plus and O2 minus, so this is CuO. And I have dinitrogen trioxide. This is a molecular compound, so they're telling me 2 N's and 3 O's. I actually want to come up here and find the oxidation number of the N so that I know what to do on the other side. And so remember that oxygen is negative 2, that would be a total of negative 6. The nitrogen would be positive, 6 divided by 2, so this is going to be plus 3, okay? On the other side, I'm going to get a polyatomic ion, which is going to be combined with the copper. So it's going to be Cu2 plus, and then the polyatomic ions you know with nitrogen are either nitrate or nitrite. Okay, so when I do that, it might be easier for you to do the oxidation number from the ion at this point. So I'm going to come in here, and this has to be a nitrogen, which is what we're hoping to keep, but we need to know is positive 3, so we're going to use that as our variable. And 3 times negative 2 for the oxygen, and this time, because the total charge is negative 1, it has to equal negative 1. So my 1 nitrogen is going to be equal to, this is negative 6, I'm going to move it to the other side, my nitrogen would be plus 5. So it's not nitrate. If I look at nitrite, this is going to be 1 nitrogen plus 2 times negative 2 for the oxygen has to equal negative 1. And now you can see that the nitrogen would equal positive 3. So this is my choice. So the formula of the compound is going to be Cu2 plus and NO2 1 minus. Means I need 2 nitrates, or nitrites, excuse me. So it's going to look like that. And now I need to come back in and balance the equation. So it better be balanced, because right now I have 1 copper on each side and 2 nitrogen on each side, and then I see 4 oxygen, so it's already balanced the way it is. All right, those are the hard ones. So now let's go learn some other ones that will be a little bit easier for you as long as you memorize them. Carbonates, if it's metal carbonate, you can follow the same rule. This is a metal with a polyatomic ion, and so you could say I'm going to get a metal oxide and a non-metal oxide, and since it's carbonate, the non-metal oxide would be carbon. Or you can memorize this as a separate rule. So the ammonium carbonate, however, is a rule all by itself. So let's go through here. Ammonium is NH4 1+, carbonate is CO3 2-. This means that I'm going to have NH4 twice CO3, and I get ammonia, which now you should know is NH3, water you should know is H2O, carbon dioxide you should know is CO2. So I don't need to do any charge balancing because they're all molecular. And now I just need to add coefficients to balance the equation. So I see 2 nitrogen, so I'm going to start here. And hopefully that fixes everything. Let's go see. So that gives me 6, and 2 more is 8 hydrogen, and I have 8 there. I see a 1 carbon, I see 3 oxygen, and we're balanced. So all we needed to do is that. In the second example now, this is going to be your metal carbonate forming calcium carbonate. I hope you're stopping the video here to add these examples. If you're not, please make a practice of that. So cadmium carbonate is a metal carbonate, and cadmium, you should know from the periodic table, is 2+, carbonate is 2-, so this would be CdCO3. I'm going to get a metal oxide. That metal has to be cadmium, so that would be Cd2+ and O2-. They're balanced, so that would be CdO, and carbon dioxide, which you know is CO2. And because the charge of this is 2+, 2- everywhere, this is already balanced, so I'm finished with that equation. Memorize these rules, people. Okay, now we're going to switch to mostly some other decompositions, and then we'll talk about backwards and forwards, okay? So let's do the decomposition of a chlorate. Remember, chlorate is ClO3 1-. So a chlorate is a compound that has chlorate as its anion. We do metal chlorates, so these are ionic compounds, and we get a metal chloride plus oxygen. This is most of your decompositions that are compounds actually form 2 small compounds, that are compounds with polyatomic ions actually form 2 small compounds, but this one, the oxygen comes out all by itself. So this is a lot easier to remember if you kind of set it apart as its own. I'm going to go ahead, chromium 3 and chlorate, ClO3 1-, gives me Cr parentheses ClO3 3. And when I decompose it, I'm going to get chromium chloride. So this would still be chromium 3, and chloride is 1-, so that would be CrCl3, and oxygen, which is diatomic. And now I need to come in and add coefficients. I see 3 chlorine and 1 chromium, but 9 oxygen and 2 oxygen. So remember, when you have an odd number on one side and an even on the other, you have to double stuff. So let's double this, which means I have to double this. That takes care of 2 chromium, and 3 times 2 and 3 times 2 is 6 chlorine. Now I have 18 oxygen, so this is going to be 9 O2. Okay, let's keep going. There are other special cases that you need to remember, and this is because in double replacement reactions, if we form carbonic acid, sulfurous acid, or ammonium hydroxide, they actually don't stay in that form in solution, they decompose. So these are 3 that you must be on the lookout for as you're doing double replacement reactions later. So I want to train you the decomposition of these now. Just so that you know, they all form water plus something else, and the something else is the balance of everything else in the compound. So let's practice our acid formula writing. Carbonic acid comes from carbon 8. So this would be CO3 2-, which means I need 2 H's. So this would be H2CO3. I'm going to get water. And notice that when I pull the water out, that accounts for both hydrogen and one of the oxygens, which leaves behind CO2. For sulfurous acid, this comes from sulfite, which is SO3 2-, so this would be H2SO3. And again, I'm going to get water and whatever else is left behind. So 2 hydrogens and an oxygen come out, leaving me with SO2. Finally, ammonium hydroxide is NH4 1+ and OH 1-, so this is NH4OH. And it decomposes into water and ammonia. And if you don't know ammonia, you can tell me the balance of it. You can see that if I pull out 2 H's, that leaves me, and an O, that leaves me with an N and 3 H's. And these are automatically balanced because everything goes into that second product. All right, another one to memorize separately is the decomposition of hydrogen peroxide. Hydrogen peroxide is H plus and O2, 2 minus. And so the formula for hydrogen peroxide is H2O2, and you get not hydrogen and oxygen. This is, if you had water, you would get hydrogen and oxygen, H2 and O2. But because this is hydrogen peroxide, that peroxide ion acts differently, and you get water and oxygen gas. And it's got to be O2 because it's oxygen by itself. So now to balance the equation, I have an odd number on the right, so I need to double this, and that means I need to double this, and now I have 4 oxygen on the left and 4 on the right. Okay, so that's the basic rules. I do want to remind you that you can work these backwards as well. So if you know a synthesis rule, you can also decompose it. Okay, so I'm going to do a few examples, and then you'll have lots of opportunity to practice this on the practice from the packet. But I do want you to see how this works. So aluminum sulfate is a salt with a polyion, which means that it came from a metal oxide and a non-metal oxide. So I have to decide what those two are in order to decompose it. Aluminum is Al3 plus and sulfate is SO4 2 minus. So I'm going to do Al2 SO4 3 as the formula of the compound. I need to get a metal oxide, so the metal has to be aluminum, and oxide is 2 minus, so this would be Al2O3. And then the non-metal oxide, the non-metal has to keep the same oxidation number. So let's look up here at the oxidation number of SO4 of sulfate. So this would be -2 equals 1 sulfur plus 4 times -2 for the oxygen. So this is -8. I move it to the other side. That gives me +6. So in here, the sulfur is +6. That means that when I put it with the non-metal oxide, it has to be S +6 with oxide 2 minus. So this is going to be SO3 to balance the charges. And then finally, I need to come back in and put coefficients in to balance the equation. So I see 2 aluminum, I see 3 sulfur, so I'm going to put a 3 in front of the SO3. Hopefully everything works now. So this is 3 times 3 is 9 plus 3 more is 12, and over here is 12. Okay, let's do this also. Decomposition of phosphorus acid. So this came from phosphite. So this would be H3PO3 because, oops, hang on. Let's talk about why. Phosphite is PO3 3 minus. So this is going to be H3PO3. Remember that to form an acid, this was a non-metal oxide plus water. So I'm going to get a non-metal oxide plus water. My non-metal oxide is going to have to be some phosphorus oxygen compound, and I have water. There are some tricks for this, but I am going to show you the oxidation number again. So in H3PO3, it's a neutral compound. So it has to equal 0, and I have 3 times +1 for the hydrogen, and the phosphorus that I'm looking for, and 3 times -2 for the oxygen. So this is -6 and +3. That means that this has to be +3. So when I go to put it in the formula, this is going to be +3 and -2. So this is going to be P2O3. And now I can put in coefficients to balance the equation. So I see 2 phosphorus. That gives me 6 hydrogen. And hopefully that balances everything else. I have 6 oxygen on the left and 3 more on the right. Okay, and then finally, if I'm going to synthesize hydrogen peroxide, remember hydrogen peroxide decomposed into water and oxygen. So if I have H2O plus O2, it should form H2O2. And to balance the equation, remember I have the odd even. I'm going to double that, and that should fix it. All right, so this is a lot to remember. So please make sure that you took really good notes. Make sure that you think about the forward and the backwards as you do this. And you are going to be practicing from the packet. Make sure that you're looking at your task list so that you know which practice goes with this. All right, good luck.